This video will introduce you to limits. So before we do anything else, please pause the video and do these warm-up problems. Okay, so for number 1 and 2, I'm hoping that these were relatively easy, unless you made sign mistakes are usually what people make on this. So for f of negative 2, you should get negative 1. You're basically just substituting in negative 2 for x. For f of 2, for number 2, f of 3 is going to be 4. You substitute in 3 for x. F of 4 is going to be 5. You end up getting negative 1 also. Okay, so hopefully you got those two right. 3 is a little bit weirder because if you substitute in 1 for x, you get 0 over 0. Actually, this one, f of 1 does not exist. So you can write the empty set if you want. You can write does not exist. I sometimes will write a sad face because it's sad. But whatever you're going to do, we do know it does not exist. Probably on the AP test, don't write the sad face, by the way. I would go with the empty set there. Okay, so that actually is where we're going to begin with limits. So a limit is the value that a function, which by the way we usually call f of x, but the value that a function approaches as its input, which we usually call x, approaches a value. Sometimes you'll see things like t or g of x, but it's generally going to be x and f of x. So you might realize that we cannot evaluate f of 1 as in number 3 in the warm-up. However, we can find its limit. So we know we can't find f of 1. And we know that this is true because if we do f of 1, we end up getting 1 squared minus 1 over 1 minus 1, which is 0 over 0. When you get a form such as 0 over 0, that's the main one actually we'll be seeing, we call this an indeterminate form. So the one that we usually see in this class is 0 over 0, but occasionally you'll see like an infinity over infinity. We'll talk about that later. But we say that 0 over 0 is indeterminate. So we've already discussed that we can't find f of 1. What we can find is the limit of f of x as x approaches 1. So I'll actually write that out because I want you guys to know how to actually speak using the math terms properly. So we say the limit of this function as x approaches 1. So when we work with limits, we have two things that we're actually going to be using in this class to find limits. For now, there's going to be a few others in the future, but that will probably be at least a month from now that we worry about the other methods. The first method that we're going to use is graphing. The second method that we're going to use, I'm going to write this to find limits, is going to be algebra. So let's start with finding limits using a graph. So in order to graph this, first thing you're probably going to want to do is figure out if you have asymptotes, if you have holes. Actually, this one is going to have a hole at x equals 1. We get that by setting x minus 1 equal to 0. So we know that there's a hole. The other thing about this is that other than that hole, it actually is going to look like the graph of y equals x plus 1. So I'd recommend you pause and try to graph it on your own. So this graph is going to be a straight line. Intercept is at y equals 1. The y-intercept's at y equals 1. And then, like I said, there is a hole at x equals 1. So we're going to have a straight line, but there's going to be a hole right here. So if you look at this graph, you hopefully notice that if you try to evaluate f of 1, it does not exist. There is no value at f of 1. However, what we can do is evaluate the limit at 1. So the limit is going to be found by looking at x equals 1. You want to know what y value is the graph approaching from both sides. And you'll find that from the right side and the left side, the graph is approaching 2. So just to reiterate, the way that we know what this limit is because when x equals 1, the graph of f of x approaches 2 from both sides. So you might have noticed in the previous slide, I did mention that for our limit, we were looking at approaching 1 from both sides. Actually, you'll notice I have these little plus and minuses here. They look kind of like exponents, but they're not. What they mean is that I have a one-sided limit. So the first one, if I have a positive, this is going to be the limit of f of x as x approaches a from the right-hand side. And you might be able to guess that the bottom limit is the limit of f of x as x approaches a from the left-hand side. All right, so we have a big example of evaluating limits based on graphs. So I tried to give you pretty much every single possible thing you might see with a graph in this problem right here. There's a very good chance you will have something like this on your next quiz, so I do recommend that you pay attention to this. So you can either pause and try it on your own, or you could just watch me do it. So let's start with number 1, the limit of f of x as x approaches 2. Actually, as x approaches 2, you're going to find that we are going to hit 3. There's nothing weird going on this one, which is really nice. Pretty much everything else that we're going to have here is weird though, so you're going to see what happens now. So now we're finding the limit as x approaches 5. So when x equals 5, you can count over, we're going to be right here. You'll notice two things. First of all, there is a hole in the graph. The second thing is that we have a weird little point below the hole. So actually, the limit is not going to be based on where that point is. The limit is going to be based on the behavior of the graph. If you look at this graph right here, this point right here at y equals 2, that's actually going to be where our limit is. Our graph is approaching 2 from both the left and the right. So that the point down at -1, the only significance of that is if I ask you to find f of 5, that's going to be the answer for that one. Okay, so number 3, the limit as x approaches 4. This is another nice one. It's pretty straightforward. It's going to be where the graph hits at x equals 4. It'll be the y value, which is going to be 1. The next one, we have the limit of f of x as x approaches -3. This one's kind of a weird one because both sides of the graph are just going down forever and ever and ever. Actually, even though it's not shown on the graph, there is an asymptote here. So just keep in mind that graphs don't always show the asymptotes, but it doesn't mean that they're not there. So because both sides of the graph are actually exhibiting the same behavior. They're both approaching very, very, very negative values. We do actually have a limit here. We say that the limit here is negative infinity. Okay, next one. The limit of f of x as x approaches negative 1. This is another weird one. So at negative 1, we have what's called a jump discontinuity in our graph, meaning that it jumps from negative 2 to positive 2. Actually, in this case, our limit does not exist because from the right side, our graph is approaching 2. From the left side, our graph is approaching negative 2. So we say it does not exist, which we write as D and E usually. Feel free to write D and E on any of my tests. Feel free to write it on the AP test. Or if you'd prefer, you can write out all the words does not exist. But every calculus teacher knows the notation D and E, so it's fine if you write that. All right, so we've already established that the limit as x approaches negative 1 doesn't exist. However, we have one-sided limits that do exist. So the limit as x approaches negative 1 from the right side, that means that we're going along on this graph, we're going along, and we hit x equals negative 1. That is going to happen at positive 2. So that one does exist. The next one, the limit as x approaches negative 1. Same idea, we're going along from the left side, and we hit at x equals negative 1, where we get closer and closer and closer to negative 2. Okay, so next one. You're welcome to try this on your own if you kind of feel like you're getting the hang of this. So for number 8, the limit as x approaches 6 of f of x, that one you'll notice from the right side and the left side we're not going in the same direction. We're not exhibiting the same behavior. So that one does not exist. So I'm going to write D and E. So for number 9, the limit as x approaches 6 from the right side, from the positive side, is going to be, it's going along like this, and it's hitting negative infinity. It's getting more and more negative. For number 10, the limit as x approaches negative 6, there should be an f of x here, by the way. You can't just take the limit of nothing. So the limit as x approaches 6 from the negative, from the left, it's going to be going along. It goes on forever and ever and ever. By the way, there's another asymptote here that isn't shown, but it doesn't mean it's not there. That is going to be positive infinity. So we're going to do our first algebraic limits. These ones are, you'll see, are not very hard. They're actually going to be really, really easy. We're going to evaluate these using what's called direct substitution. And direct substitution means that we are just going to plug in the number. So the limit of x minus 2 as x approaches 3, we're going to find this by substituting in 3 for x. You just get 1. For number 2, this one looks a little bit harder because the 5 has a plus sign, meaning it's a right-hand limit. However, because x squared minus 4 is continuous at x equals 5, it doesn't actually matter if we have a plus there, if we have a minus there. The answers will all be the same. If it was not continuous, which you would know if it had like a denominator or where like x minus 5 in the denominator, it wouldn't be continuous, then there would be other things that we would have to do. But in this case, it's continuous, so we're just going to substitute in 5. And when we do that, we just get 21. For 3, people sometimes, in the future, you might be one of these people, they freak out when they see a limit and they have a denominator. However, in this case, we have the limit of this function as x approaches 4. If you substitute in 4, we are not going to get anything undefined, so it's going to be pretty straightforward. Don't try to do anything fancy on this one. you end up getting 10 over negative 4, which gives you negative 5 halves. So the last thing I want to talk about with limits is this theorem. So basically what this theorem is saying is that if you have a left-hand limit and a right-hand limit equal to a value, then the overall limit equals that value. If they're not equal to the same value, the limit will not exist. So I wrote this out more in English. So the limit only exists if the left side and the right side limits are equal. And if you want an example, if you look back at in this video, if you look at the graph at numbers 5, 6, and 7, you'll notice that the limit does not exist because the left side and the right side limits are not equal.